So, we will continue. So, we discussed CDFs, properties of CDFs. So, we said that CDFs have 4 fundamental properties. They start off at minus infinity, they start off at 0, end up at plus 1 at plus infinity, and everywhere in between it is monotonically non decreasing, and they have to be right continuous. Right. Conversely, I also orally mentioned that if you give me any function at all which has these 4 properties, it will be the CDF of some random variable. Okay. So, this converse result, the proof is available in Grimmett and Sturzeker, for example. You can explicitly construct a random variable. So, given any function with these properties, you can explicitly construct a random variable whose CDF is the function you want. Okay. So, these 4 are the only fundamental properties, so to speak. There are no more properties that generally define a random variable CDF. Okay. So, today we will move on to types of random variables. Okay. So, remember that a random variable, so you are looking at some probability space omega f p, right, and the real line sitting here, and your random variable maps each elementary outcome to a unique real number x of omega, right. So, this will be x of omega. What we said is that pre images of Borel sets are f measurable, and that essentially implied that there is a probability law p x, right, from the Borel sigma algebra to 0 1, which is a probability measure on RBR, right. Effectively the random variable pushes the measure p onto the real line, and you have a measure, induced measure is p x, probability law p x. Now, you classify random variables as belonging to various types based on the nature of measure induced on the real line, namely based on the nature of p x. Okay. Now, I have to tell you what nature of p x is, what do you mean by how many types of measures there are and so on, right. So, it turns out that there is a very fundamental theorem in measure theory that says that there are only 3 fundamental types of measure on the real line. Any probability measure on the real line will have to be are only fundamentally of 3 types, or they can be of some combinations thereof. Okay. So, you are already familiar with 2, I believe, right. So, one is what you call a discrete random variable, right, that is something you are used to. There is, and then you are also used to what is known as a continuous random variable, right. These things I will define very precisely, but you for now you know colloquially roughly that you know that there are discrete random variables and continuous random variables, and you also know that you can have a mixture of these 2, right. That mixture is not a fundamental type of a random variable, right, it is just putting this and that together, right. You can put on maybe on a discrete set you put some probability, and on some and then you put some probability on some interval or something. Now, there is actually a third fundamental type of probability measure on the real line called a singular measure, singular random variable. Okay. The singular random variables you probably would not have encountered so far, for the reason they are perfectly valid probability measures. They are neither discrete nor are they continuous. In fact, they are not mixtures either. There is a fundamentally new type of a probability measure that you would probably not have encountered so far. Okay. The reason is the reason you do not really encounter them so much is they are mostly of academic interest, they are very bizarre. Okay. They do not have any useful applications in particular, right. So, there are totally 3 types of, so there is discrete random variables, there is continuous random variables. I have not defined any of this, I am just speaking it out. Okay. And then there is a third fundamental type called singular random variable. And there is a very basic result in measure theory called Lebesgue's decomposition theorem, which says that all probability measures on R, any p x you consider, will have to be only one of these three type or mixtures thereof. Okay. So, how many types will you get totally? So, you can have this or that pure, or you can have these two together, these two together, these two together, or all three together in general, right. So, any measure on any probability measure on R can in fact be decomposed into a discrete component, a continuous component and a singular component. Okay. This is what this famous theorem called Lebesgue's decomposition theorem says. Okay. This is not a theorem we will prove, okay. It is something that it is just good to know. I mean, again it is a fairly mathematical result and you will not worry so much about it. All we need to know is there is no more, there is only these three fundamental types and mixtures thereof. All measures, probability measures on R only fall into these three categories or mixtures thereof. Okay. So, there are 7 types of random variables on R, okay, not 3, you are used to 3, right. Discrete, continuous, mixtures of discrete and continuous. In fact, there is one more fundamental type of random variable called singular random variable, which you would not have encountered because it is very bizarre and not very practically useful, but it is nevertheless a valid probability measure, singular random variable. Are there any questions? I have not told you what they are, right. I mean, I have defined one by one, I will define. So, shall we move on to discrete random variable? So, the nicest type of random variables are discrete random variable, just like the easiest type of probability measures were discrete probability spaces. So, discrete random variables are also the easiest to study. Okay. So, a random variable x is said to be discrete definition. If there exists a countable P subset of R so a countable Borel set. Okay. So, this must be Borel. Well, so what did I say? Discrete random variable, if there is a countable, actually this is a countable set, so it is automatically Borel. So, I do not even have to say this. So, such that what do I want to say, P x of E equal to 1. Okay. So, actually I do not even strictly have to say this because it is implied by the fact that it is a countable set, E all countable sets are Borel, right. So, I was about to say OE has to be Borel because I am talking about its P x, but the fact that it is countable means it is automatically Borel, right. That is all there is. Okay. So, what is a random variable? What is a discrete random variable? It is a random variable which puts all its probability, the probability of 1 rests on a countable set. Okay. So, there exists some countable set E whose pre image has probability 1, right. Okay. See, the one little the way see I could have see I did not quite say that the range of the random variable is countable, right. Also I mean that is also not terrible, that is also an okay definition, except that this definition allows for some measure zeros, some points of measure 0 here being mapped to outside E also, right. So, there exists some countable set E whose pre image is not necessarily a sample space, but some set of probability 1, right. That is what that means. Okay. which means with probability 1 the random variable takes values in a countable set, right. Yes. The only difference, yeah. So, I was so let me say, in other words, x takes values in a countable set almost surely, right. With probability 1 it takes values in a countable set when it takes. So, you can write E as let us say E 1 E 2 dot 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 is a countable set after all, and with probability 1 it only takes those discrete set of values, right. There may be some omegas which in some set of probability 0 which takes values outside the set E, which is why I did not say that the range is necessarily just a countable set, right. They are almost the same, but not quite the same, because there could be some measure 0 set here, right, some measure 0 set here which maps outside E, right, but as long as it has probability 0 it is okay.
So, in the perspective of discrete random variable, the sample space is now the same as that omega.
The sample space is omega. So, this is a random variable x. So, this is a random variable from omega to r as usual. Okay. So, what I am saying is that it is a discrete random variable if the set of values it takes in R belongs to a countable set with probability 1, that is it.
For px to be measured, the px of omega should be 1.
Px of omega, no, Px is only defined for Borel sets, subsets of R, right.
To satisfy the measure theory, probability measure as a theory, probability as a measure, we have to put px of omega sample space equal to 1.
Correct.
So, what sample space we give?
Px of not sample space, Px of R is 1, right. Px of R is always 1 because it is a probability measure on R. I am saying that all that probability rests on, see this R has probability 1, there is no doubt about it because it is a probability measure. I am saying all that probability rests on a countable set, right. So, the probability of the random variable taking values outside this countable set is 0, okay, which is a little bit different from saying that the range of the random variable is only countable, slightly different because you could have some 0 measure sets which map to outside E, right. Fine, is this clear to everybody? So, in particular if you write E, see E is a countable set, so it has a listing, right. So, if I write E as E 1 E 2 dot dot dot, it could be finite or countably infinite. If it is finite I will write E 1 E 2 E n, it is countably infinite it is E 1 E 2 dot dot dot, let us say it is E 1 E 2 dot dot dot, then I essentially have that Px of E is 1, right. So, but Px of E, see these are all singletons, right, these EIs are just real numbers, right. So, what can I say? So, P of Px of E can be written as the sum of Px of these singletons. Why? So, yeah, because it is countable, countably additive, no. So, of course, I am assuming that the EIs are distinct, okay. If you just write EIs belong to R, distinct, right. So, then you have Px of E which is 1, right, is equal to sum over I Px of what? The singletons EI, right. So, in other words this can be written as sum over I equals 1 through infinity probability of omega. So, this is probability measure on R, I can transfer it to the probability measure on the original sample space and write probability of omega such that x of omega equal to E I, right, but I will no longer write that, I will only write x is equal to E I. Okay. If you want, you write, I mean if you prefer x I, you can write x I here. Okay. X is equal to x I is probably a little nicer, right. Okay. So, this discrete random variable has all the probabilities sitting on this countable set, and there is some, and if you specify the probability of each of the singletons values that it takes, you essentially specified the entire measure right, entire probability law, right. So, if you give me any Borel set on R, what would it be? What would be its probability law, I mean probability P x. So, for any B in B, P x of B under this particular discrete measure will be sum over how do I write this, sum over all the I such that E I belongs to B, probability that x is equal to E I. I just have to, this is a complicated notation, I am simply saying that you look at all the E I's that exist in your Borel set, simply add their probabilities. Okay, that is all you need to do to find the probability measure of any Borel set. Okay. Is that clear? Any questions?
So, discrete random variable is a constant. If I use it a constant, because if I take omega is equal to 0 1 and then script f is Borel space, there is a uniform measure of 0 1. So, can we just define discrete probability measure?
You can define a discrete random. So, omega can be anything. See, omega does not have to be countable or uncountable or any such thing. I am just saying that the random variable has to take values in a countable set with probability 1. So, you could have omega can be 0 1 for example, but the random variable could simply be some indicator random variable for example is clearly a discrete random variable, right, because it only takes 2 values, right. So, you can have indicator of any set on 0 1, so any Borel set on 0 1, that will be a discrete random variable, right. So, omega can be uncountable also, no problem. So, is this okay? So, generally, so if you specify this, right, then you are basically specified the probability law completely, because I have explicitly written down the probability law for every Borel set in terms of that guy, right. So, this thing is called the probability mass function. Okay. So, definition. The function little p x, which is equal to the probability that x is equal to x, is called the, so this is for p x of x, p x of little x, okay, is called the probability mass function of x. See, this definition you can make for any random variable, right. I mean, I am just, so after all x is equal to x is a, I mean this is a singleton set and you can always talk about its probability. and you can define the probability mass function for any random variable, nothing stops you from doing that. But for a discrete random variable, the nice thing is that the probability mass function completely specifies its probability law, right. So, if x is discrete, so what we have shown here is that if x is a discrete random variable, the probability mass function, this is PMF, completely describes the probability law of x as we have shown here, right. You should probably just write this down here, okay, because it specifies the probability of any Borel set, right. So, this for the values that it does not take, so this will be 0. I mean, if outside the set E, right, this guy will be 0, no problem, right. You can define it for all real numbers, but it will only be non-zero for these EIs, okay. You can define it for any kind of a random variable. I am just saying that for the discrete random variable, it captures everything there is to capture about the random variable. For continuous or singular, it will not capture, actually it captures almost nothing, okay. If the probability law, probability mass function only captures the probability law for discrete random variables. Okay, so that deals with the probability law. How will the CDF of a discrete random variable look? It will have a number of steps, right. So, it will be it will have several discontinuities. So, if you are trying to plot for this random variable, so if I try to plot f x of x against x, so maybe my EIs are like that, right. So, may just for so if my E4s are like my E's are like that, then it will start off at 0 and at each point it will jump by an amount p x of EI, right. So, it will, let us say that there is nothing here, there is no EIs here, just for the sake of argument, then this guy will start from 0, jump solid dot here, hollow dot here, right, remain flat until you see the next E I and again jump solid dot here, hollow dot here, so on, right. Here again jump, hollow dot, jump, that is it, right. This is how the, so and that will be 1. If it is, I mean I am only plotting for finite number of EIs, right, but if there are countably many EIs, countably infinite EIs, then there will be countably infinitely many discontinuities, right. Okay. So, that is how typically how a CDF of the discrete random variable looks. So, I usually see the, if you specify, so on the height of each of these jumps, for example, this jump will be p x of E4, right. So, each jump corresponds to the probability that x is equal to that EI, right. So, if you specify the PMF, you can get the CDF, right, because you simply put in that much jump. This is the CDF capital F x, right. See the mass function is, you can define it for all x, it will be 0 except at the EIs where it takes value equal to p x of EI. it will not have jumps, it will simply be like sticks, right? It will just be like a discrete, right. All right. So, remember, see, I mean this discrete random variable can actually be fairly complicated in the sense that this E could be rationals. In that case, it is not nicely separated sticks standing everywhere, right. You could have a distribution over the rationals, right. It may not be as simple as you think, it may not be as nice as you think here, right. You can put some measures on the rationals in 0 1, right. You can do it if you want, right. For example, if you want to put a measure on the rationals in 0 1, one valid probability measure would be to simply arrange the rationals, call q n your nth rational in 0 1 and say the probability x is equal to q n is equal to some 1 by n square or something like that, appropriately scaled, so that it adds up to 1, right. That is a discrete random variable, right, because all the probability measure is on the rationals. See what I am saying, but your CDF will not, CDF will be very bizarre, it will not be like this, right. You have to, it will jump at all these rational points, correct. So, although you are used to some nice discrete CDFs like this, but discrete random variables can also be a little bit counterintuitive or bizarre in the sense that it may not look like nice steps going up. But the random variables that are practically used often are in fact quite nice, the discrete random variables. So, I will give some examples. If there are no more questions on the theoretical bit, I will give some examples. So, you will notice that I have deliberately been avoiding examples, right. So, I want to keep a certain level of abstraction going, so that you get the abstract understanding first, right. You can always give examples later, but I want that abstraction to keep that thread to be going all along, right.